Well, Rob, let's talk a little bit about load cell outputs and specifically signal conditioned outputs. Not everybody can use a load cell that has a simple analog millivolt per volt output. So, what can a person do that needs something other than millivolt because that's the way that their system is configured. Their system is looking for a different type of sensor input.
Right, Mark. I think when somebody comes to us for that, not that standard millivolt per volt output that comes with all load cells, and they're talking with our R&D team, and they tell us maybe they know, or sometimes maybe they're not sure. So do I need that 4 to 20? Do I need that 0 to 20 or something, close to that? What's going to work best for them with the sensor that they're going to purchase from us? So, they're sitting there, okay, we need it and we're not sure exactly. So we'll work with, as I said, our R&D team, particularly electronics team, to decide what output is going to work best for them in that application. So where do we need amplified application? Well, mainly for applications for overload protection and lifting devices, cranes, draft pins, and elevators, is a great example. In all of these cases, the load cell output is fed directly into the user's PLC.
Okay. So, and a PLC can't accept a millivolt per volt. That's just incompatible with typical PLCs.
Exactly. So, some people then, if we take a step back, go, well, wait a minute, do I need, if I'm going to have a, say, 4 to 20 milliamp output, do I need a special load cell? No. If you look at most of the standard VPG load cells on our website, or even custom load cells that we make for a lot of our OEMs, we can adapt this amplified, output to any load cell that we have. So a question that I have, though, more technically based, for you is, does this amplified output affect the accuracy of my load cell?
That's a great question. And the answer is pretty simple. It's no. And that's because the amplified signal is just a pass through. It's just a direct conversion of the millivolt into the 4 to 20 or 0 to 10 type of amplified signal. So it works hand in hand with the output and therefore the same accuracy.
Okay. As far as location of an amplified board, are we able to embed it in the cavity of the load cell? Is this something downstream? From things that you've seen over the years, we have options with that, correct?
We do. The 4 to 20, 0 to 10 amplifier is quite small. It's about the size of a quarter, for instance. And if a load cell is, a little bit bigger than a quarter and we've got a little bit of room, we can certainly embed it right in the load cell. It makes for a real clean package because that 4 to 20 or 0 to 10 is going to come right out of the load cell. If the load cell is smaller and there's just no physical room to put it in there, we can put it downstream. So it's somewhere outside of the load cell itself and on the cable between the load cell and where the output signal is going to tie into the PLC.
Okay. So again, if somebody does think that they require an amplified output when they're talking to us about their application, whether it maybe be an industry standard application, but specifically a custom, this is something that comes up in the beginning of the conversation and that we discuss it in the design stage, correct?
Right. And the thing that 4 to 20 offers is what they call a powered loop. So you've got a continuous loop of 4 to 20 milliamps that's happening. So at zero load, you have a 4 milliamp signal. So you get a confirmation that the load cell is working. If you have zero output and your amplifier simply says 0, you don't know if something has failed and it says 0, or if there's simply no load on the load cell, but it's still functioning. So the 4 to 20 solves that problem because you get 4 as your 0 balance, your 0 baseline. And then it's also good for a very long cable run because you've got this powered loop constantly providing the amperage in a circular path from the load cell to the PLC from its excitation source. You don't have any loss of signal due to increased resistance over a long cable run.
Good information. Thanks a lot, Mark, for the discussion.